Hello everyone, today we'll be discussing more about or maybe trying to understand more about what is vertical circular motion and how to find velocities at different positions of vertical circular motion. So let me consider a body which is tied to a string. So imagine this is your string, this is the center from where the string has been tied, this is the body having some mass mg. Okay, let us consider the mass as m. So basically what I'm trying to do is I'll be performing a vertical circular motion. So I'm drawing the vertical circle with the help of dotted lines. Okay, pardon me for my handwriting. So this will be the vertical circular motion which is happening. Let me say at this moment the velocity of the particle will be obviously tangential. Since you guys have an idea, if you guys have an idea about circular motion, you guys know that the velocity will always be tangential to the circle. The radius is equal to the length of string. I am naming it as r as of now. So the velocity at this position, let me call it as vt, calling it as velocity at the topmost position. Similarly, when the particle comes to the bottom, the velocity at bottom becomes, let me call this velocity as vb, calling it as velocity at bottom. Okay, again the radius will be r, the length is not going to change. Okay, so if I'll try to draw, this is topmost position, this is bottommost position. Okay, so if I'll try to draw a free body diagram at this position, I can clearly say that, see, in this case mg is acting downward and the tension along the string will also be acting downward. Let me call this tension as tt, tension at top. Okay, now since we are very well aware that at topmost position or maybe at any position, whichever forces are directed towards the center, they will be behaving as centripetal force. Let us let us consider that these two forces, they are going to behave as centripetal force at this particular position. So the equation goes like this. In this case it will be mg plus tension at top will be equal to centripetal force, that is mv square upon r. You will have to make sure that you write vt square so that the v clearly specify that the velocity at top and at any position will be not same, they will be different. Okay, so yep, this is one condition where I can easily figure it out that tension at top will be equal to mvt square upon r minus mg. Okay, so this expression is quite important while solving the numericals related to vertical circular motion. Now coming back, if you consider the bottommost position, or maybe before going to the bottommost position, I'll give you what do we say, a special case. Like if someone is asking what will the minimum velocity at which the circular motion can happen. So minimum velocity, in order to find minimum velocity, you need to find minimum tension, because clearly you can see that greater the velocity, greater will be the tension, because the other factors cannot change. Lesser the velocity, lesser will be the tension. Now if you are intending to find least or maybe the minimum velocity, you will have to consider minimum tension, and the tension minimum can be just above 0. So if you're considering for Vt minimum, the tension will be approximately equal to 0. Okay, it is not exactly equal to 0, it is just above 0. We will consider approximately equal to 0. You substitute the tension's value in this equation, you can see that mg will be equal to, after that you can see that mg will be equal to m Vt minimum square upon r. Okay, m gets cancelled, this will give me r and the square root taking the other side, Vt minimum will be equal to, you're taking r on the other side, you're taking the square on the other side, you'll be getting square root of rg. So this is the expression of minimum velocity which you will have to maintain in order to perform vertical circular motion. That means if you can maintain this speed at this particular position, automatically the body will perform vertical circular motion and come back to its original position, considering that there is no air resistance due to which it can lose any amount of energy. Okay, now let's proceed further. This was all about topmost position. Now coming to the bottommost position, the next consideration. Okay, so speaking about bottommost position, I'll be drawing free body diagram at this particular position, so you can easily figure it out that mg will be always acting downward. But in this case, the tension, in previous case the tension was also downward because it was acting along string. Here also it is acting along string, but it will be upward. So this will be tension at bottom. Okay, so tension at bottom, yeah, this is tension at bottom. So considering this case, as again you have to consider the same imagination in order to find tension's expression. Any forces along the radius towards the center is termed as centripetal force. Here I can say tension is along the radius towards the center, whereas mg is away from the center, due to which I can say that TB minus mg, since they are opposite in direction, will be behaving as centripetal force. That means they can be categorized as mvb square upon r. That means tension's expression can be termed as TB is equal to mvb square upon r plus mg. See, from here, from these two expressions, you can come into one conclusion that tension at topmost position mv square by r minus mg and tension at bottommost position is mv square by r plus mg. Clearly, we can see that tension at bottom will be greater than tension at top due to two reasons. One is here we have positive mg, here we have negative mg, and the other reason is definitely velocity at bottom will be much greater than velocity at top. Okay, yeah. So coming back. Since we have found what is the minimum velocity of at topmost position, let us try to figure out what can be the minimum velocity at bottommost position. Before figuring out the minimum velocity, I'll give you a general expression of the bottommost position's velocity. Coming back, you consider law of conservation of energy. So according to I'll write down the short form law of conservation of energy. Okay, so you conserve the energies of bottommost and topmost position. So the conclusion says that kinetic energy at topmost position plus potential energy at topmost position will be equal to kinetic energy at bottommost position plus potential energy at bottommost position. So if you are considering the bottommost position as the ground, okay, so here the height will be 0. In the center the height will be considered as maybe r, and at the topmost position the height can be considered as 2r. Okay, provided you are considering the bottommost position as height equal to 0. Yeah, coming back, so kinetic energy at topmost position can be, you guys are very well aware about the kinetic energies formula, that is half mvt square plus potential energy at topmost position will be mgh, where h will be equal to 2r, that is mg multiplied by 2r is equal to kinetic energy at bottommost position will be equal to half mvb square. Okay, and potential energy, since we don't have a potential energy, we simply write it as 0 because the height at bottommost position is considered as 0. Now you cancel m's. You are intending to find velocity at bottommost position. Simple ideology, you cancel these halves, and in order to balance you multiply a 2 over here. You'll be getting v square plus 2 into 2 4 rg is equal to vb square. That means vb square will be equal to vt square plus 4rg. Okay, so this is a general expression for velocity at bottommost point. Okay, now since we were discussing about the minimum velocity required at the topmost position, the corresponding minimum velocity at bottommost position can be determined very easily with the help of one simple idea, that is, instead of vt, that is, this is the general value of vt, we have found that whatever is the value of vt square plus 4rg will give you the velocity of the vb square, that is bottommost velocity square. So once you substitute the minimum velocity of topmost position over here, the corresponding value will be nothing but the minimum velocity at bottommost position. So finally, minimum velocity at bottommost position can be expressed as rg plus 4rg is 5rg. The square goes over there, gives us square root. Okay, pardon me for my handwriting. So we have found the minimum velocity as topmost position. So whenever you intend to perform a vertical circular motion, either you'll have to make sure that the topmost position's velocity is at least or maybe some value greater than root rg, and bottommost point's velocity is some value greater than root 5rg or maybe equal to root 5rg as well. So I believe you have a clear understanding. I have discussed the tension at bottom point and tension as topmost point as well. Okay, now coming to another consideration, again I'm drawing the same diagram over here. So again drawing the vertical circular motion. Okay, here is the vertical circular motion, here is the center. Imagine you have your body at this particular position. Now at this particular position, if you wish to determine how much will be the tension of the body or some other values, okay, so if you wish to determine the tension, it's very simple. You'll have to first define at which position it is. So in order to define the position, I'm using the concept of angle with vertical. let me say the tension. Obviously the tension will always be acting along the string. Okay, here I have mg. Since this is theta, I can resolve mg into two components where this will also be theta due to corresponding angle theorem. Since this is theta, I can say that this component will be mg cos theta and the other component will be mg sin theta. Okay, now simply I can say, if I'm considering that this body is moving with a velocity of v, then I can simply say that, again the same logic we have to use. The forces acting along the center towards along the radius towards the center will be termed as centripetal force. That means T minus mg cos theta will be equal to mv square upon r. As simple as that. This will give you T is equal to mv square upon r plus mg cos theta. Now if at all, see, if you have the value of cos theta, it's well and good. If you don't have the value of cos theta, it's not a big deal. You simply have to they'll give you some amount of data. If they are giving you what is the height, for example, if they are giving you what is the height, okay, so I'll use another pen for just clarification. Okay, if they are giving you what is the height from bottommost point or maybe ground, you simply have to figure out how much is the height. Okay, you guys are very well aware that this total length is r, which means this particular distance will be r minus h. Okay, so why did I do this? And similarly this particular length will be r. Okay, from here what do we understand? This is cos theta. Cos theta is nothing but adjacent upon hypotenuse. Adjacent is nothing but r minus h upon r. So here instead of cos theta you can simply substitute adjacent, that is r minus h upon r hypotenuse, if they are giving you what is the height. So with the help of this expression you can easily determine what is the tension at any random point. That is, this is a random point. That means at any point all over the vertical circular motion you can easily determine how much will be the tension. And if you have the velocity of bottommost point, velocity of the circular motion at bottommost point, by law of conservation of energy you can easily determine what can be the velocity at this particular point. I'll just show it to you for you guys. Okay, according to law of conservation of energy, kinetic energy at bottommost point plus potential energy at bottommost point is equal to kinetic energy at any random point plus potential energy at any random point. This will give me kinetic energy at bottommost point is half mvb square plus potential energy at bottommost point is 0. Kinetic energy at any random point will be half mv square plus potential energy at that random point is mgh. You can take m common and cancel them. So provided you need to have the value of h. If you don't have the value of h and if you have the value of theta, with the help of cos theta you can easily find the value of h as well. Anyway, so yes, h is pretty compulsory in this case. So if you need to have v, definitely you'll have to isolate everything. What we can do, we can cancel half, and in order to balance that half you can multiply 2 over here. Take this to the other side, your expression goes like this: v square is equal to on the other side we have vb square minus, you're taking this term, these terms on the other side, that is 2gh. So with this I am concluding the lecture. So just a small recap. In this lecture we started with the introduction towards vertical circular motion, then we came to know what can be the tension at topmost point, what can be the velocity, minimum velocity required at topmost point, what can be the tension at bottommost point, what can be the velocity, general expression for the velocity at bottommost point, what can be the minimum velocity at bottommost point. And then we considered a random point where we found how much can the tension be, and similarly how much can the velocity be. I hope this lecture was fruitful to you. Kindly subscribe my channel for more videos. Thanks a lot.